Welcome to Tomorrow Unveiled, your shortcut to being well-informed on the cutting edge of space exploration and technology. This week, we're taking a deep dive into the really groundbreaking developments from July 11th to 18th, 2025. Stuff that's shaping our future beyond Earth. Our dedicated research team pulled together a stack of incredible sources, articles, research, expert analyses, and well, our mission is to pull out the most important nuggets for you.
Absolutely. And this past week, it wasn't just, pure science discovery. It was really about seeing foundational technologies get validated, get deployed, things that are essential if humanity is going to have a sustained presence off-world. We'll be looking at advancements that are showing up across multiple reports, signaling a real pivot, I think, from just ideas to actual implementation.
Okay. Let's kick off then. Let's unpack the strides being made and just getting to space and, what we're building once we're up there. One thing that really jumped out at us from the research was this incredible reusability milestone. SpaceX hit its 500th Falcon 9 launch, 500, and what was it, the 472nd first stage recovery?
So,
That's right, 472 successful landings. It's monumental.
it sounds huge on paper, but what does that actually mean, like beyond the number? Are we seeing that translate into real economic impact for the wider industry, or is it still kind of theoretical for most people?
Oh, it's very real. The profound takeaway here isn't just cheaper launches, though that's part of it. It's fundamentally reshaping the business model of space. Think about it like the shift from custom-built cars to mass production. Suddenly, space isn't just for governments or the super rich. It's becoming a viable platform for countless commercial ventures. We're seeing huge demand for satellites, for in-orbit services, all driven by this access, this kind of operational reliability from commercial players. It's a total game changer.
Okay, so Falcon 9 milestone, that's impressive for getting stuff up there. But what about people? We also saw that NASA's Crew 11 mission coming up soon is flying on the Dragon Endeavour capsule, and this will be its 6th trip to orbit, the record.
So how does that kind of reusability work for human spaceflight? What does a spacecraft that could fly, up to 15 times potentially, what does that really signify for having people live and work in space long term?
You've hit on a key point. This is a critical step in de-risking those future deep space missions. To the moon, to Mars. The International Space Station, it's increasingly being used as this vital engineering testbed. By showing how durable these modern crew capsules are, by enabling longer stays, NASA is just systematically buying down the risks, both the physiological risks to the astronauts and the operational risks for the missions themselves. It's proving the hardware is tough enough for the long haul.
Got it. So rockets are more reusable, capsules are more reusable, pushing down costs, extending time in space. But hang on, all those launches need somewhere to, launch from, right? And it seems like the ground infrastructure, the spaceports, that's suddenly becoming a surprising bottleneck.
That's exactly right.
Our research team flagged new legislation, federal and state level in Florida, for example, making it cheaper to raise capital for spaceport development. Why now? Why is the ground suddenly so critical?
Well, if you zoom out a bit, the sheer increase in launch frequency, driven by companies like SpaceX, has put enormous strain on the existing facilities. Launching multiple times a week wasn't the norm even a few years ago. Now it is. So the ground infrastructure, it's emerged as the primary constraint. This legislation shows a broader understanding that these spaceports are just as vital for the 21st century.
As seaports and airports were in the 20th.
Precisely. Without robust ground support, we just can't take full advantage of this cheaper access to orbit we've been talking about.
Okay, so we're getting better and cheaper at getting to space. Makes sense. But what about when we're actually there? The next big thing seems to be building things in orbit. Is that fair to say?
I think so, yes.
Our research team highlighted what sounds like a landmark international collaboration, 3D printing a functional metal thruster on the ISS.
That's right, a 1-Newton thruster. Small, but precise, used for fine-tuning orbits.
It really does sound like science fiction becoming reality, printing engine parts in space.
And the critical thing here isn't just printing something, it's printing a functional component. This project goes way beyond just a proof of concept. It demonstrates the whole value chain for in-space manufacturing, what people call ISM. It's powerful validation really for the business case for future orbital servicing hubs. Imagine repairing or upgrading satellites right there in space.
Wow.
It's about closing the loop, creating a truly self-sustaining space economy eventually.
And it's not just spacecraft parts, is it? We saw reports about commercial ventures like Varda Space Industries. They raised significant funding recently to speed up robotic drug manufacturing in space.
Yes, that's another fascinating area.
Now, when I hear making drugs in microgravity, my first thought is just, okay, maybe it's pure, but is there more to it? What's the real advantage? What problem does this solve that we can't solve down here?
Well, purity is part of it, but the real aha moment with microgravity drug manufacturing isn't just about optimizing existing drugs. It's about the potential to form molecules or stabilize crystal structures that simply cannot be made effectively on Earth because gravity interferes. So you're potentially unlocking entirely new classes of therapeutics.
Ah, okay. So not just better versions, but completely new possibilities.
Exactly. That's the transformative prospect for medicine. And the fact that investors are putting serious money into companies like Varda shows that this is moving from theory to a practical industry.
Right, shifting from concept to practical reality. And it's not just manufacturing techniques, it's new materials, too. Something else that jumped out was a consortium in Japan, JAXA involved, developing a new copper base shape memory alloy. And the kicker is, it works at an astounding minus 200 degrees Celsius.
Yeah, that's incredibly cold, cryogenic temperatures.
What problem does a material like that solve? Why is functioning at that extreme temperature such a big deal for space missions?
It's an elegant solution for missions going way out, deep space, outer solar system, or maybe permanently shadowed craters on the moon where it's unbelievably cold. This alloy allows for simple, passive mechanical actuators, things that can move or change shape just based on temperature without complex electronics or motors.
So less complexity, less power needed.
Exactly. That means significantly better reliability, and you cut down on mass and the power budget. It just removes a massive design headache for those kinds of missions.
Interesting. And the research also mentioned this material has direct uses back here on Earth in green energy, particularly for liquid hydrogen.
That's right. Liquid hydrogen is extremely cold, so materials that perform well at those temperatures are crucial for storage, transport, and use in things like hydrogen fuel cells.
It's always exciting to see that direct feedback loop space tech helping solve problems down here.
Yeah.
Okay, let's shift gears a bit. Connectivity, that's obviously key to everything we do on Earth and beyond. The data we looked at showed really rapid advancements in direct-to-device satellite comms, D2D. Basically, satellite signals straight to your regular smartphone.
Mm-hmm.
Rogers, in Canada, for instance, launched a public beta for satellite-to-mobile text messaging, including text to 911. That feels like it could be a massive deal for safety in remote areas.
It absolutely is.
Yeah.
This is a perfect example of what some are calling the lifeline tier of DTD services. It provides that immediate, incredibly valuable basic connectivity, emergency texts, maybe basic messaging. But at the same time, you've got projects like MDA Space UK's Skyfi mission. They're working on the next level, the integration tier.
Okay, what's the difference?
They're developing regenerative 5G payloads. Regenerative means the satellite actually processes and boosts the signal on board. It's not just a simple bent pipe relaying the signal. This allows for much stronger, more seamless, high-performance mobile broadband, like an extension of the terrestrial network.
So, moving beyond just emergency texts to actual usable broadband, potentially anywhere.
That's the goal, a massive step towards truly ubiquitous coverage.
And talking about coverage, the mega constellation race is definitely full steam ahead. We saw Amazon's Project Kuiper launch its first production satellites, and they launched them on a SpaceX Falcon 9.
Yes, that raises a few eyebrows.
I mean, given their direct competitors in the satellite internet space, that's like, I don't know, Coke buying bottles from Pepsi, because Pepsi just happens to have the best bottling plant right now. It seems incredibly pragmatic.
It is. And what's really compelling there is Amazon's strategic calculation. They have these urgent regulatory deadlines they need to meet, deploying half their constellation, over 1,600 satellites, by July 2026. Clearly, meeting that deadline outweighed any sort of corporate rivalry in the short term.
So it underscores just how dominant SpaceX currently is as a launch provider.
Absolutely. It shows they're a critical enabler for the entire low Earth orbit economy right now, even for the companies they compete directly against. Sometimes practical business logic just trumps everything else.
Right. Okay, maybe the most thrilling communication news, though, was this historic first optical communication link with a deep space spacecraft, NASA's Psyche probe, and established by European Space Agency ground stations, an international interplanetary optical link.
A truly historic moment. That optical handshake, as some called it.
What does this actually mean for the future? How fundamentally could optical laser-based communication change interplanetary missions?
I think this marks a fundamental philosophical shift in how we think about deep space communication. It's a crucial step towards creating a standardized, high-bandwidth solar system internet, if you will,
Hmm.
by proving that hardware from different agencies, NASA spacecraft, ESA ground station, can talk to each other optically over these vast distances.
Sets a precedent for interoperability.
Exactly. It lays the groundwork for a future where missions can send back vastly more scientific data, high-definition video from Mars or Jupiter or the asteroid belt, not just the trickle we often get now. This will dramatically boost the science return from missions and give us much more flexibility in how we operate them. It's a complete transformation for deep space exploration.
We love hearing your thoughts on all this. Whether you're on YouTube or your favorite podcast app, definitely leave a comment and let us know what you think about this week's space news. And if you're finding this insightful, maybe take a moment to like this video, subscribe to Tomorrow Unveiled right here on YouTube, and be sure to turn on notifications so you never miss an update on the future.
Yes, and if you happen to be listening on a service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and a review for Tomorrow Unveiled. It really does help us reach new listeners who are curious about these topics.
Okay, so these advancements are undeniably exciting, but of course they come with challenges. One major concern our research team flagged repeatedly is orbital crowding, space traffic management, especially with these mega constellations rapidly filling up low Earth orbit. What happens if we don't get this right? Is it just about avoiding collisions, or is it more complicated?
It's definitely more complicated, though collisions are the most obvious risk. The real question becomes, how do we stop ELEO from becoming a kind of Wild West? With potentially tens, maybe hundreds of thousands of active satellites eventually, the risk of collisions, yes, but also radio frequency interference. It just keeps increasing. And a major collision could create debris clouds that threaten access to space for everyone for generations.
Right, the Kessler syndrome idea.
Exactly. So initiatives like the EU's proposed EU Space Act are trying to get ahead of this, to harmonize safety rules, debris mitigation standards. It reflects a really pressing global concern. We need to manage this environment responsibly, protect those orbital highways.
And alongside the crowding, we're also seeing interesting geopolitical dynamics playing out, like Europe's Invictus program. Our team highlighted this effort to develop a Mach 5 aerospace vehicle, hypersonic.
Yes, a reusable hypersonic platform.
What are the dual-use implications there? Is the challenge simply that civilian tech like this inevitably blurs the lines with military applications, making international norms harder? Or is it more about specific military uses?
Well, it's really both. This Invictus program represents a very deliberate strategic push by Europe to secure sovereign capabilities in reusable hypersonic systems. Now, while it's often framed in terms of civilian space access, maybe a reusable first stage or rapid point-to-point transport, the development of vehicles that can reliably travel at Mach 5 has direct, significant applications for defense. Think reconnaissance, potentially strike capabilities.
So it inherently blurs those lines.
It does. It makes it harder to differentiate intentions and capabilities, which certainly influences the global strategic balance and, yeah, complicates future arms control efforts.
And speaking of strategic capabilities, China achieved the world's first satellite-to-satellite orbital refueling demonstration.
A major technical feat, yes.
On the one hand, that's huge for sustainability, extending satellite lifespans, saving money, makes total sense economically. But does that capability not sort of raise a few strategic eyebrows, especially given the current geopolitical climate and the focus on competition in space?
Precisely. It absolutely does. From an economic standpoint, it could revolutionize space operations, keep valuable assets working longer, make constellations more resilient, immense potential benefits. However, if you look at the broader strategic picture, mastering orbital refueling also significantly enhances military flexibility. It allows satellites to maneuver more without worrying about running out of fuel, potentially repositioning surveillance assets, or maybe even interfering with other satellites covertly.
So it intensifies that international competition.
It definitely intensifies competition in critical space capabilities and, yes, raises questions about strategic advantage in both space-based services and military operations. It's about who can sustain their assets in orbit longer and with more flexibility. That's a significant factor in space power.
So looking ahead then, our research team projects that within the next, say, 12 to 24 months, we're going to see a lot of these prototypes and demonstrations move rapidly towards becoming actual products and operational systems. What's the biggest strategic takeaway from that rapid evolution for the global space industry? What should listeners really grasp about this accelerated pace?
I think the most enduring breakthroughs, the things with the biggest long-term impact, are the underlying enabling technologies. We're talking about revolutionary propulsion concepts, these novel manufacturing processes like the 3D printing and new materials, advanced alloys, and of course the next-gen network architectures like optical comms and D2D. Strategic advantage, long-term, will belong to those nations and companies that truly master these foundational technologies. They're defining the next generation of all space systems.
So it's less about the individual satellite or mission and more about mastering the building blocks.
Exactly. And beyond just the tech itself, we're seeing this trend of co-opetition, like the Amazon SpaceX launch, and a real push for interoperability becoming strategic imperatives. It's
Yeah.
about building a space ecosystem that's robust, resilient, maybe even collaborative in some ways, because the challenges are just too big for any one player to solve alone.
What an incredible week it's been to track. I mean, from breaking records in reusability, proving out in-space manufacturing.
Connecting the cosmos with lasers.
Yeah. And navigating this really complex strategic landscape that's unfolding in orbit. It honestly feels like we're not just watching the future happen anymore. We're actively building it, turning yesterday's sci-fi into tomorrow's reality.
I agree. The convergence of all these different advancements, it really signals a fundamental shift. Space technology is moving from being experimental, niche, to being operational at a truly planetary scale. We really are witnessing the dawn of a true cislunar economy, that sphere of economic activity and infrastructure developing between the Earth and the Moon. And the focus now is squarely on sustainable, permanent human presence beyond Earth.
It's a profound shift, which leads to a final thought, perhaps something for you or listeners to ponder. As humanity's reach does extend further, as we start setting up more permanent bases, maybe on the moon, maybe beyond, what new forms of governance, what new kinds of international cooperation are we going to need? How do we ensure that this expansion leads to a peaceful and prosperous multiplanetary future for everyone? Something to think about.